Welcome back. This is session 2 of Large Language Models, Words as Vectors. Last time, we mapped out why language is so hard for machines, and we ended on a specific, concrete failure. The machine's representation of a word carries no meaning at all. Today, we fix that. Today, you'll see how a machine can learn, from raw text alone, that cat and feline belong together. And the answer turns out to be one of the most beautiful ideas in the whole field. Before any theory, let me show you the punchline first. I want you to see the destination before we walk the road. King minus man plus woman. And no, this isn't a riddle. It's genuine arithmetic done on the machine's representations of those three words. Before the answer appears, take a guess. Queen. The machine says queen. Is that what you guessed? Nobody told it that queens are female royals. Nobody gave it a dictionary or a single grammar rule. All it ever did was read text, billions of words of it, and learn to predict which words appear near which. And somehow, out of that one humble task, arithmetic on meaning became possible. By the end of this session, you'll know exactly how that happens, and you'll also know precisely where it breaks. Here's the destination in picture form. What does success actually look like when a machine has learned to represent words well? Watch this. Cat, dog, wolf, fox, bear. The animal words have landed together, one tight neighborhood in the space. And a quick word about what you're looking at. The real space has hundreds of dimensions, so this is a flattened, two-dimensional picture of it. How the flattening works, I'll tell you near the end. Nobody labeled these words as animals. The machine just noticed they show up in the same kinds of sentences. Now the countries. France, Germany, Italy, Japan, a completely separate region. Text about countries follows its own patterns, so the countries drift together, away from the animals. Now, look at the middle of the map. King, queen, prince, duke. A little royal court of their own. Coffee, tea, bread, wine, down here. You can probably predict what happens next. And the numbers. Look how tight that cluster is, the tightest of all, because numbers appear in extremely regular contexts. 5 regions. Each dot is a word. Each region is a concept. And nobody defined a single one of them. Meaning has geometry. That's the claim of this session. And our job today is to understand where that geometry comes from. But first, the villain. Remember the closing figure from last session? One hot encoding on the left, that mysterious cloud of clustered words on the right? Let's now give the left side the full autopsy it deserves. This is one hot encoding, the standard old way to hand a word to a machine. Cat gets its own dimension, a 1 in the cat position, zeros everywhere else. Simple, clean, and as you're about to see, completely hollow. Dog gets its own dimension. You see the pattern, a different spike in a different position. And here's feline, a cat in every sense that matters. But look at its vector, a 1 in a totally unrelated position. To this representation, feline is exactly as different from cat as house is. House. Same story again. Every word gets its own private axis, and notice that no word shares anything with any other. And run completes the picture. Now stretch this in your mind. A real vocabulary has 50,000 words, so each of these rows is 50,000 cells long, all zeros except 1. Here's the killer. Measure the similarity between cat and feline the standard way, with a dot product. 0. Not small, exactly 0. And you'd get the same 0 for cat and government, or cat and refrigerator. Every pair of words, total strangers. 50,000 dimensions, 49,999 zeros per word, and not one drop of meaning in any of it. That's the problem, laid bare. Let's give this villain its proper name. The orthogonality problem. In one hot space, every word sits exactly as far from every other word. Synonyms, categories, analogies, the entire structure of language, and none of it can even be written down here. You can't teach the machine that cat and feline are close, because in this space, close doesn't exist. So here's what we actually need. A space where similar words sit close together, where the geometry itself carries the meaning. The question is, close according to whom? Who decides that cat and feline belong together if no human is allowed to label anything? The answer comes not from computer science, but from linguistics, and it predates all of this by decades. J.R. Firth, a British linguist, wrote this in 1957 in A Synopsis of Linguistic Theory. You shall know a word by the company it keeps. Sit with that for a second, because the whole session hangs on it. Look at coffee, and look at the words that travel with it in real text. Hot, drink, morning, cup, warm, bitter, aroma, brew. That ring of neighbors is coffee's company. Now, tea. Look at its ring. It's the same ring. Coffee and tea keep almost identical company, and that's no accident. Words with similar meanings get used in similar surroundings. Coffee and tea share no definition. They share a neighborhood. And here's the leap that makes everything work. That neighborhood can be counted. It's sitting right there in the text. No labels needed. The company a word keeps is the training signal. So let's put the plan together in 3 steps. Step 1. We represent every word as a dense vector, not 50,000 dimensions of nearly all zeros, but a few hundred numbers, every single one of them carrying information. Step 2. We arrange those vectors so that words with similar company end up close together. Cat near feline. And then we've done something quietly profound. We've turned a language problem into a geometry problem. Machines are hopeless at what does this word mean, but they're extremely good at move these points around until nearby means related. That's a problem gradient descent can solve. Nobody went from first sentence to working software overnight. It took 57 years, and I want you to see the relay race, because each runner hit a wall that the next one broke. 1957, Firth states the distributional hypothesis, the quote you just read, a linguistic idea, pure theory, decades before anyone had the computing power to act on it. 1990, latent semantic analysis from Scott Deerwester and colleagues, the first serious attempt to compute with Firth's idea. You build a giant word-by-document co-occurrence matrix and crush it down with a technique called singular value decomposition. Dense vectors do emerge, and they genuinely capture some meaning. But here's the wall this runner hits. It's slow, it's memory-hungry, and updating it with new text is a pain. 2003, Yoshua Bengio and colleagues publish a neural probabilistic language model. Here's their breakthrough insight. Let a neural network learn dense word vectors as a side effect of learning to predict the next word. Conceptually, that's the modern recipe, and you'll recognize it in everything we build today. But on 2003 hardware, it's painfully slow, and it can't reach web scale. 2013, and here's where it catches fire. Tomas Mikolov, with Ilya Sutskever, Kai Chen, Greg Corrado, and Jeff Dean at Google, publishes Word2Vec and NeurIPS. The core idea is Bengio's, but engineered ruthlessly for speed. Strip the network to almost nothing, add the sampling tricks we'll meet in a few slides, and suddenly you can train on billions of words overnight. This is the paper the king-man result comes from. And 2014, Pennington, Socher, and Manning at Stanford published GloVe, taking the global count the whole corpus road instead. We'll give it its own slide near the end. 2 different mathematical routes, and remarkably, they arrive at nearly the same place. So, how does Word2Vec actually work? The whole thing rests on one sneaky move, and I want you to catch it. Train a small neural network to predict a word's context. Show it a word, ask it which words are likely to appear nearby. Then, throw the predictions away. Keep the weights? You might be thinking, why train a network whose output you don't even want? Here's the trick. To get good at predicting coffee's neighbors, the network is forced to store something about coffee internally. And whatever it stores for tea must end up similar, because tea has the same neighbors. Those internal weights are the vectors. The prediction task was a pretext. The representation was the point all along. Word2Vec comes in 2 flavors. The more important one is called skipgram. Given the center word, predict its surroundings. Let's build the machine piece by piece and watch how small it really is. We start with one word, sat, as a one-hot vector. 50,000 numbers, one of them a 1. Yes, the same hollow representation we just spent 2 slides attacking. Stay with me. It's about to become something better. First transformation. Multiply by a matrix W with 1 row per vocabulary word and D columns. And notice what multiplying a one-hot vector by a matrix actually does. It just pulls out 1 row. Row lookup, nothing more. That row, D numbers, is the embedding of SAT. The hidden layer holds those D numbers, around 300 in practice. This little vector is the thing we're actually here to learn. Then, a second matrix, W prime, expands those 300 numbers back out to 50,000 scores, 1 per vocabulary word. Watch where this box goes at the end of the slide. Its fate is the sneaky move I promised. And a softmax turns the scores into probabilities. Given SAT, how likely is each word to appear nearby? We train the network to put high probability on the words that actually did. So in plain words, the whole forward pass is look up a row, multiply by 1 matrix, softmax. That's the entire network. No deep stack, no convolutions. The shallowness is deliberate because shallow means fast and fast means more data. Every training step nudges the weights so the real neighbors score a little higher. Billions of nudges across billions of positions in the text, and you never label a thing. And when training ends, we throw away W prime and the softmax entirely and keep W. Every row of W is now the dense vector for 1 word. Everything else was scaffolding. Where does the training data come from? This is my favorite part, because the answer is from nowhere. No annotators, no labels, no cost. Take any sentence you like. The cat sat on the mat. Right now, 6 neutral tokens, no position chosen yet. Pick a center word, SAT. That's the input to the network. With a window size of 2, look 2 words left and 2 words right. The, cat, on the. These 4 are the targets the network should predict. Count what we just harvested. 1 position, 4 training pairs. SAT predicts the, SAT predicts cat, SAT predicts on, SAT predicts the. Now slide the window 1 word to the right, and on becomes the center. 4 more pairs. Every position in every sentence hands you a tiny supervised example that nobody had to label. Slide it across all of Wikipedia, all of the news, billions of words of the web, and you've got billions of training examples for free. That's the quiet revolution here. The text is its own teacher. Hold on to that idea, because it comes back in session 7 as the training recipe for GPT itself. I said Word2Vec has 2 flavors. Here's the second, quickly. Continuous bag of words, CBOW for short. Picture skipgram reflected in a mirror. That's the whole idea. Instead of center predicts context, we flip it. Given the, cat, on the, fill in the blank in the middle. The 4 context words are the inputs now. Each one gets looked up in the embedding matrix, exactly the row lookup you already know. Then, all 4 embeddings are simply averaged into 1 vector. That's the bag in the name. We throw away the word order and just blend the context together. The blended vector runs through the same kind of output step you saw in skipgram, and we train the network to rank SAT at the top. Same matrices, reversed objective. So which one should you use? Skipgram does better on rare words because each rare word stars in many training pairs of its own. CBOW just trains faster. And when people say Word2Vec, they usually mean skipgram. One engineering problem stands between this design and those billions of words, and I want you to see the fix because it's pure pragmatism. The bottleneck is the softmax. To say how likely is each neighbor, the network computes a score for all 50,000 vocabulary words at every single training step. Billions of steps times 50,000 scores. That's the wall. So Mikolov's team changed the question. Forget scoring the whole vocabulary. Just answer yes or no. Is this particular pair real? Did coffee really appear next to morning? Yes. That pair came from actual text. Did pterodactyl? No. We sampled that word at random as a fake. The network just has to tell real neighbors from random imposters. You might be thinking, surely a crude yes-no game can't teach the same rich geometry as a full softmax. Remarkably, it can. For each real pair, sample about 15 fakes. 15 comparisons instead of 50,000. The embeddings come out just as good, and training gets orders of magnitude faster. That's negative sampling, and it's the single trick that made Word2Vec practical at web scale. So you train this thing on billions of words. What actually ends up inside those 300 numbers? 4 things, and the last one should worry you. First, semantic similarity, the thing we set out to get. Cat, dog, kitten, land together. River, stream, brook, land together. Similar company, similar vectors, exactly as first promised. Syntax, which nobody asked for. Run, ran, running, hold the same relative positions as walk, walked, walking. The network was never taught grammar. Grammar showed up anyway as geometry. World knowledge. The arrow from Paris to France points the same way as Berlin to Germany and Tokyo to Japan. It read no encyclopedia. It inferred geography from patterns of company. And bias. The same mechanism that absorbs geography absorbs prejudice. If the training text associations link doctors with men and nurses with women, so will the vectors, and any system built on them inherits it silently. We'll face this head-on in session 14. For now, just remember, the space learns everything about the text, including the parts we're not proud of. Time to pay off the opening. King minus man plus woman. You now know enough to see exactly why it works. 4 words, 4 points in the space, placed by training. So far you see nothing but positions. Now draw the arrow from man to woman, and the arrow from king to queen. Look at them, same direction, same length. That shared arrow is the gender relationship, encoded as a consistent offset. Man to king, woman to queen. Look, 2 parallel arrows again, and that direction is royalty. Relationships between words have become directions in space. So here's the arithmetic as geometry. Start at king. Subtracting man and adding woman applies the gender arrow. Follow it, and where do you land? On queen. Not because anyone programmed monarchy into the machine, but because parallel company produces parallel arrows. So the point is this. The famous demo is nothing more than offsets staying consistent across word pairs. You're looking at a parallelogram in 300 dimensions. In one sentence, in a well-trained embedding space, relations are directions. And honestly, a caution. This parallelogram trick is the showpiece example, and it works beautifully for it. Plenty of analogies come out fuzzier. Your lab includes hunting for the failures. Let's go back to the picture we started with, because you can now read it with completely different eyes. The same map. But now you know where every cluster comes from. Animals cluster because animal words keep animal company. Numbers huddle tightest because numbers live in the most rigid context of all. Every cluster is a neighborhood of shared contexts, discovered by a row lookup network playing fill in the blank. One honesty note before you take this picture too literally. The real space has 300 dimensions. To print it, an algorithm called TSNE squeezes it down to 2. Distances inside a cluster survive that squeeze. Distances between clusters mostly don't. So trust the huddles, not the gaps between them. The map was learned, never labeled. If you keep one sentence from today, keep that one. 1 year after Word2Vec, a Stanford team, Jeffrey Pennington, Richard Socher, and Christopher Manning, published a different route to the same destination at EMNLP 2014. You saw their stop on the history timeline. It's called GloVe, for global vectors. And the name is the criticism. Word2Vec, they argued, peeks through one tiny window at a time and never sees the whole corpus at once. GloVe isn't a prediction model at all. It's matrix factorization, the mathematical descendant of that 1990 LSA idea from our history slide, but with a much better objective. Step 1. Read the entire corpus once and build a giant table X, where entry ij counts how often word I appears near word j. All the company statistics in one matrix up front. Step 2. Find word vectors whose dot products reproduce that table. Roughly, wi.wj should approximate the log of the count. Words that co-occur a lot get vectors that point the same way. And if you're wondering about pairs that never co-occur, log of 0, well spotted. GloVe's objective simply weights those entries out. It's Firth again, just written as an equation. So, Word2Vec nibbles through local windows with a neural network. GloVe swallows the global counts with linear algebra. Different maths entirely. And the embedding spaces they produce, nearly interchangeable. When two unrelated methods land on the same structure, that's usually a sign the structure was really in the data. Side by side then, before we hit the wall. Here's the whole table in one look. Prediction versus factorization, local windows versus global counts. Skipgram handles rare words better, because each occurrence mints its own training pairs. GloVe edges ahead on analogy benchmarks. Both give you dense vectors of a few hundred dimensions. And for most tasks, the honest answer to which one is, it barely matters. And these vectors didn't stay academic, not for a moment. For years, embeddings like these ran quietly inside search engines and recommender systems, matching your query to documents by geometry, not keywords. And file this away for session 12. When we build retrieval augmented generation, the retrieval half of every RAG stack is exactly this idea, meaning as geometry, all grown up. Let's take stock of the space we've built, with one more level of nuance than before. Meaning, with a wrinkle worth knowing. Antonyms. You say the coffee is hot and the coffee is cold, in exactly the same kinds of sentences. So hot and cold sit close together, differing along a particular direction rather than being far apart. Nearness in this space means shared context, which is usually, but not always, shared meaning. Syntax. Systematically. Notice the walk-to-walked offset matches run to ran and jumped to jumped. Tense, plurals, comparatives, each one a consistent direction. World knowledge, capitals, currencies, nationalities, all aligned as offsets. And remember, no encyclopedia anywhere, company alone. And bias, again, because it belongs on every honest inventory of this space. Gendered job associations, cultural stereotypes, they're in the text, so they're in the geometry, as directions you can literally measure. Keep that image. It returns in session 14. Now we hit the wall. Everything we've built today has one fundamental flaw, and I want you to feel it before I name it. I deposited money at the bank. Remember this word? Bank was our very first example of lexical ambiguity back in session 1. It has come to collect. I walked along the riverbank. Same word, completely different meaning. A financial institution, a strip of riverside ground. Every language you speak is full of words like this. So, what does Word2Vec do with bank? Think about the machinery you now understand. One row of W per word. One row. So bank gets one vector, pulled toward money words by half its sentences and toward river words by the other half. The result is a blurred average that represents neither meaning well. The more senses a word has, the muddier its vector. Here's the villain of this session, named at last. Static embeddings are context-free. One word, one vector forever. The vector for bank is identical in every sentence ever written. And after session 1, you know that context is everything in language. We've built a beautiful map of words, and the map cannot see the sentence it's being used in. So, the question this session leaves open is this. What if the same word could get a different vector in every sentence it appears in? Bank near deposited, money vector. Bank near river, ground vector. Computed fresh, every time, from the sentence itself. But look at what that requires. Reading the whole sentence, maybe the whole paragraph, before deciding what one word means. A sliding window can't do that. A fixed row of W can't do that. We need machinery we simply don't have yet. Session 6. BERT will answer this. Representations that change with context. But to get there, we need the architecture that makes it possible. The transformer. And that road runs through sequences, attention, and 3 sessions of work. The villain stays loose for a while. Remember its name when we finally corner it. Let me place today on the map of the whole course. 14 stops. Session 1, done. We know why language is hard. Session 2, today. Words have geometry now. We've beaten the representation problem, the first villain from last session's closing figure. And here's the shape of the road ahead. Foundations where we still are. architecture where Bert is waiting with our answer to polysemy, and the real world, one session at a time. Next session, the obvious follow-up question. Every word is a vector now. Fine. A sentence is a sequence of them, in an order that matters. How does a machine read a sequence and remember what it read? That sequence is in memory, and it has a villain of its own. Your lab this week. Get your hands on real vectors in 5 parts. Part 1. Build a co-occurrence matrix from scratch on a small corpus. You'll watch raw text turn into the counts everything else stands on, before any learning happens. Part 2. Train an actual Word2Vec model with GenSim. You choose the window size, the dimensions, the epochs, and you'll see how each choice changes the space. Part 3. Explore what you trained. Ask for the nearest neighbors of any word. Run king minus man plus woman yourself and see what your model says. Part 4. Project your space down to 2 dimensions with TSNE and compare your clusters to the map from today's slides. And the challenge. Break it. Find the analogies that fail, the words with senses blurred together, and work out why. Data problem, window problem, or the polysemy wall itself. That's where the real learning is. See you in session 3.